Hey everyone, let's practice a little bit of synthesis, namely applying some of the things we've learned about additions to alkenes to chemical problems. And so to do this, let's take a look at question 9.58 in your book, which asks you to be able to propose a concise synthesis of this alkene, which is a trisubstituted alkene, 1, 2, 3 groups attached to it, to this disubstituted alkene, effectively walking the double bond over by one carbon. And so the way to do this, at least the way that I like to think about this, is let's think. Let's work backwards actually. What can we do to this alkene in a retrosynthetic manner? And so what we're going to do is we're going to use a chunky arrow that's going to allow us to think in a backwards direction. And so we can easily envision making this alkene from an alkyl halide, or an alkyl leaving group. So, let's do that. Right? So, in this case, we can envision having an alkyl tosylate plus a really bulky base. So, LDA, very bulky base, that could do what's known as a Hofmann E2 elimination, which gets us the least substituted product. That being said, do we know a way of making a tosylate from our starting alkene? So it turns out that while making a tosylate is a little tough, we do know how to make an alcohol. So let's simply say that perhaps instead of directly making the tosylate, we make the alcohol instead. Which we can then make via anti-Markovnikov addition to our starting alkene. So now what we've done is, working backwards, we've come up with sort of a pathway of synthesis that's going to allow us to take our starting alkene and transform that into our desired product. So what I'm going to do is I'm simply going to put a little box around our retrosynthetic pathway, and now let's work the problem in the forward direction. First step, or the last step in our retrosynthetic analysis, is to do an anti-Markovnikov addition of water. And just to help you visualize that, I'll add in the hydrogen there, to our starting alkene. The best way we know to do this is using hydroboration-oxidation. So let's go ahead and do that. Again, the first step is addition of borane THF to the alkene, followed by the oxidative step, which is the addition of a basic solution of hydrogen peroxide. And what that will accomplish is the anti-Markovnikov addition of water across the double bond. And what that will do is that'll give us the following secondary alcohol. Okay, so now we know we need to do an elimination to form our product alkene, but in general, hydroxide, or OH here, is an absolutely terrible leaving group. So we need to convert this into a very good leaving group. And so there are a few different ways to do this. In class last term, we talked about adding an acid such that instead of OH minus as a leaving group, we have neutral water. However, oftentimes when you add acid, it's very difficult to do an E2 elimination, which is the more controllable of the eliminations. Additionally, it allows us to create our less substituted alkene product, which we've shown here. So what we're going to do is, instead of adding acid, we're going to convert this into a tosylate ester. And that's going to turn it into a very good leaving group. And so to do that, all we do is add tosyl chloride in a solution of pyridine. So pyridine is a solvent, so pyridine looks like this. It's a 6-membered ring, looks like benzene, except one of the carbons attached is replaced for a nitrogen. And so this is a good basic solvent. And what this will allow us to do is to directly what's known as protect our alcohol as a tosylate ester. But what this is going to do is turn our alcohol into a phenomenal leaving group. So in this case then, what we're going to have to do is perform an E2 elimination to give us our desired product. But we can't just do any E2 elimination. Rather, what we've got to do is we've got to do an elimination that's going to deprotonate at the less substituted spot. In other words, we're going to give an elimination that's not going to follow Zaitsek's rule, but rather is going to give us what's known as the Hofmann product. And so if you remember back from last term, to do that, we do that by treating our alkyl X group with a strong but extremely bulky base, such that it's much easier for that base to reach in and grab off one of these protons and to grab off a proton at the more substituted spot. And so what this will wind up doing is giving us our desired less substituted product, shown here. So in summary, the way we solved this problem was we first approached the problem in a retrosynthetic manner. What can we do step by step that's going to lead us to our product? So we know that elimination from an alkyl tosylate with an extremely bulky base gives us the Hofmann elimination product, which is our alkene shown here. We can produce our alkyl tosylate from an alcohol, which ultimately we can produce from our starting alkene using an anti-Markovnikov hydroboration-oxidation. So in the forward direction, we take our alkene, we do a hydroboration-oxidation to form our alcohol. We then form the tosylate ester, so make a good leaving group out of a poor leaving group by treating this alcohol with tosyl chloride and pyridine. We create the tosylate then, which we're able to eliminate with LDA or an appropriate other very bulky base to yield the Hofmann elimination product shown here. Hopefully this helps you start to bring together some of the things we learned last term with some of the additions to alkenes we learned this term to be able to make some very interesting products. So, until next time.